Hello everyone. I am Gofi Hong from Shenzhen Institute for Advanced Study, USTC. On behalf of all the authors, I am very happy to present our work. Learning robust policy for multi-UV collision avoidance via compact causal feature. Let me first give you a quick outline. I will start from the background and motivation, then describe our key insight on compact causal features, then introduce our compact causal feature learning framework, present experiments, and finally conclude. Multi-UV is broadly deployed, such as delivery, precision agriculture. In these applications, collision avoidance is essential for UV. Recently, deep reinforcement learning has become a popular paradigm because it learns end-to-end policies directly from depth images, outperforming handcrafted pipelines. However, DRL implicitly assumes the train and test distributions are the same, which rarely holds in the real world. Due to limited generalization, UVs may fail in unseen environments, leading to economic damage and threat to personal safety. So the core question we ask is, where does the generalization gap come from? To answer this, we run an experiment. We take SC-ray, a representative DRL baseline, and train it in a playground. When we test it in a forest, the swarm success rate fell to 0. We then asked, which component is failing, the visual encoder or the policy network? We fine-tuned each one separately on the forest environment. Fine-tuning only the visual encoder lifted ISR from 51.9% to 88.6%. Fine-tuning only the policy network barely changed anything, still around 48%. So, the visual representation, not the policy, is the bottleneck of generalization. Why does the visual representation fail to generalize? The encoder encodes all information from depth images, including non-causal and redundant components. For example, background is non-causal feature, UV texture is redundant feature. The non-causal feature and redundant feature may introduce spurious correlations and lead to limited generalization. The takeaway is clear. Learning compact causal features is crucial for improving the generalization of deep reinforcement learning. What are compact causal features? As shown in this figure, we divide visual features into 3 levels. Using UV obstacle avoidance as an example. First, visual features may contain non-causal features, such as background texture and obstacle shape. These features are often domain-specific, so relying on them can hurt generalization. Second, even within the causal features, there may still be redundant information, such as UV texture or details of crashed UVs. They are not directly useful for making avoidance decisions. What we really want are the compact causal features, such as obstacle distance and UV velocity. They are domain invariant and task relevant, so they can support robust decision-making in unseen environments. Therefore, our goal is to extract these compact causal features in 2 steps. First, identifying causal and non-causal features. Then compress redundant information. This is the architecture of our CCFL framework. It has 2 stages. In stage 1, we focus on representation learning. The V encoder extracts visual features, while the causal feature identification module disentangles causal features from non-causal ones through contrastive learning. In stage 2, we perform policy learning with SC. Within the actor network, we introduce the redundancy feature compression module to suppress redundant channels. Therefore, the representation fed into the policy is both causal and compact. Let me zoom in on the CFI module. Its goal is to disentangle causal and non-causal features by hard contrastive learning. First, we construct positive and negative sample pairs. Positive pairs consist of an image of a sphere obstacle in the playground and an image of a cube obstacle in the forest. They are put together because they represent the same essential avoidance behavior despite differences in obstacle shape or background. Negative pairs consist of an image of empty playground and an image of sphere obstacle in playground. They are pushed apart because they represent different collision avoidance behaviors due to the presence or absence of an obstacle. Our objective combines the HCO loss and the V reconstruction loss. So the learned representation is both invariant and faithful to the original observation. Finally, only the disentangled causal features are retained for policy learning. Even after CFI, causal features may still contain task-irrelevant redundancy. The RFC module learns a differentiable binary mask to select important feature channels and suppress redundant ones. The input feature is then refined by applying this mask. The mask is supervised jointly. The actor loss J, pi, drives it to keep task-relevant channels, while an L1 regularization on the mask promotes sparsity. If the mask incorrectly suppresses a useful channel, the actor loss J, pi, increases, prompting the mask to self-correct. To validate the effectiveness of CCFL, we built a benchmark based on Unreal Engine and AirSim. During training, multi-UV collision avoidance is learned in a playground scene containing only one cubic obstacle and one spherical obstacle. During testing, the learned policy is evaluated in a forest scene with 22 unseen obstacles, forming a typical out-of-distribution setting. These are our main results on the unseen forest with 22 unseen obstacles. The baseline SAC + RA achieves 0 swarm success rate. Some UVs get through, but the swarm never arrive together safely. We compared with 5 methods covering augmentation, regularization, attention, causal disentanglement, and causal feature selection. Each provides only marginal improvement on swarm success. Our CCF achieves significant improvements in SSR, ISR, and SPL, demonstrating better generalization. To verify that the results are not specific to the forest environment, we further built 2 additional unseen scenes, Snow Mountain and Canyon, using the same obstacle settings. In all unseen environments, SAC + RE drops to 0% swarm success rate. But CCFL maintains robust swarm safety and reliable individual performance. The ablation study shows that both CFI and RFC improve performance when used individually. But the best results are achieved when they are combined. To conclude, first, we find that DRL generalizes poorly in multi-UV collision avoidance mainly because visual representations contain non-causal and redundant information. Second, we proposed CCFL, a unified framework combining causal feature identification with redundancy feature compression to learn compact causal features. Third, experiments show that CCFL consistently outperforms state-of-the-art methods, significantly improving robustness and generalization in unseen scenarios. Thank you very much. I'm happy to take questions.